My name is Sajadullah and I'm a PhD student at University of São Paulo in Brazil. I would like to thank the organizing committee for giving me the opportunity to present part of my work here in this event. My topic is the preparation of layer-by-layer films of titanium dioxide using cellulose phosphate as a binder molecule. And the films also have another component, phosphotungstic acid, so I'll be briefly describing the properties of films. Most of you know that titanium dioxide is an important heterogeneous photocatalyst, and it turns photoactive under UV radiation. We have the production of a hole in the valence band, and the electrons promotes to the conduction band, both of which ultimately leads to the generation of hydroxyl species, which are very strong oxidizing agent. Because of such UV-induced photocatalytic properties, titanium dioxide has applications, perhaps the most of all the semiconductor photocatalysts. But we have some problems. For example, the electron-hole recombination. Once the nanoparticles are irradiated for a long time, we have a separation of electron-hole, but there could be a recombination inside the nanoparticles as well as on the surface. This decreases the quantum yield. Another problem is the recovery of the nanometric powder that are usually difficult to be separated even by centrifugation. To find the solution, one way is to use polyoxymetallites that are metal oxygen cluster compounds. They have very good solubility in most of the solvent, and they can accept the electron from the conduction bed of titanium dioxide, can be transferred to this species where it is reduced. And these reduced species can be reoxidized by oxygen. So we have another route to produce superoxide anion radicals, or all the production here and at this point. This can give a synergic effect to the photocatalysis, as well as lead to an increase in the electron-hole separation because the electrons are no more in the accumulated on the surface of the nanoparticles, titanium dioxide nanoparticles. The other problem of recycling can be overcome if we make films of titanium dioxide, if we immobilize them on certain substrate. But you always need to modify the surface of the substrate, or you have to use some binder or polyelectrolyte molecules. The one that we introduced is cellulose phosphate. It's used in an ion exchanger for metal cations. So we selected this one to be used as a binder. This is a very simple procedure using cellulose phosphate. You need an immersion of the substrate. The substrate could be glass, bacterial cellulose, it could be silicon. We use different substrates. It works the same in all cases. So a single immersion in cellulose phosphate followed by immersion in titanium dioxide, and you have very good layer deposition. An important point to mention here is that most of the polyelectrolyte, you need to adjust the pH of the solutions to have good favorable electrostatic attraction. But in case of cellulose phosphate, you don't need it, so it makes the job easy and very reproducible. Each time you adjust the pH of the titanium suspension, you're going to destroy your electrode because there is always some absorption of the nanoparticles of the electrode as well. So better not to involve something that, better to use a binder that doesn't involve seed steps and give you very reproducible results. The next step is in the immersion in the HPW, that is the polyoxymetallic phosphotungstic acid that I mentioned in the earlier slide. Using UV visible spectroscopy, we compare cellulose phosphate with the conventional polyelectrolyte that is called polydiallyl dilmethylammonium chloride, PDAC or PDDAC. So you see, if you have no electrolyte, there is no absorption in the particles onto the quartz plates. If we have PDDAC, we have slight absorption of nanoparticles. But in case of cellulose phosphate, there is a huge difference compared to this PDDAC, and cellulose phosphate acts as a very good binder for the nanoparticles. We studied vibrational spectroscopy, again, with an increase in the number of immersion. This vibrational moods, the titanium oxygen bond vibrational mood at 760 around in this region, it's actually a broad peak, increases. Finally, after immersion into phosphotungstic this species, we have the characteristic vibrational modes that are shown here and indicated in this figure alongside. When we compare the vibrational modes of phosphotungstic acid in the film with the pure HPW solution in the absence of titanium dioxide, we have a shift in this mood, in this oxygen atom, vibrational mood corresponding to this oxygen mood, which means that there is an interaction. And this was actually the idea. So cellulose phosphate interacting with titanium dioxide interacting with the other molecule. Looking into the scanning electron microscopy images, we see that at glass, very uniform distribution can be obtained using cellulose phosphate. We have forms on filter paper cellulose, blank fibers, and as well as covered with titanium dioxide, bacterial cellulose covered with titanium dioxide, the low magnification images, and the higher magnification images are also shown. If we compare the distribution, we use titanium X-ray mapping. In case of, when you have cellulose phosphate, you have very good distribution of the nanoparticles, but in absence of cellulose phosphate, we have agglomeration of the particles on the plant cellulose paper fibers. So it becomes clear that cellulose phosphate is not only a binder, it also helps in a very good achieving good distribution of the nanoparticles. We use transmission electron microscopy to see further into the details of the interaction we saw in FTR analysis. Again, we see the phosphotungstic acid and titanium dioxide in contact, characterized by high resolution electron transmission, which is an annotated. The interplanar distance is calculated correspond to annotation of titanium dioxide. We also study the interface, which is important for the electron transfer. I will skip this. You see that the titanium dioxide is crystalline with very well defined interplanar distances, but in this case, the interface is semi-crystalline. The shift in the titanium 2p region because of introduction of phosphotungstic acid shows the interaction again as we witnessed in FTR analysis. The photochromic response of phosphotungstic acid, because phosphotungstic acid is reduced, increases by about 35% in the presence of titanium dioxide, which shows that this interface actually has an implication. There is a transfer of electron from the conduction band of titanium to phosphotungstic acid. The photocatalytic activity, as we expected, didn't increase because we used phosphotungstic acid as a loss layer. There was a decrease in surface area, though we had separation of electron and holes. And with this, I would conclude that cellulose phosphate can be used as a good binder to make very homogeneous and adherent film of titanium dioxide on different substrates, including bacterial cellulose, silicon, glass, quartz, etc. And that's it. Thank you.
Thank you very much for all the speakers. And I ask you to the audience a round of applause for all the speakers. Thank you so much.